All right, so let's see, some announcements that you should have seen. Yeah, there's two quizzes just went up that sort of go through. One quiz goes all the way through all the isomeric relationships. So, we start with constitutional isomers, then we do conformers, and then stereoisomers. So take a look at that. That one's due Monday. There are 4 live quizzes right now. See, there's a whole bunch of stuff out there. The second quiz I posted today is absolute configuration. So figuring out RNS, we're going to do that. We did that in class on Tuesday. We're going to do some of that here today. So I have like sort of a PowerPoint we're going to go through. We'll work those problems, and then if you hang around to the end, I'll just take questions. Kind of, I'm not going anywhere. My driveway is an inch thick sheet of ice, so and I'm a coward. Anyway, we'll go through that, and then all those quizzes. The other thing I wanted to say is I posted a topic list. It's not really I don't usually put up topics. I put up like what you should be able to do, right? So the way I'm going to evaluate is, I said all along, is you're going to work problems next week. So a week from like right now, you'll be taking exam 1. And all I can evaluate is you working the problem. So I can't get into your head to like figure out concepts. So it's just what you put down. And so I frame my study guides in terms of skills you should be able to do. So it looks like a really long list, but a lot of it you've already got. I think if you go through it, you'll find you do know how to do those things. And so, as I always tell students, like, find the things you don't do all that well and work on that. All right. So we all like to. It feels good to successfully do things, right? So I always. I don't know. Like it's just we tend to practice the stuff we're good at because it feels good to be good at it. But what really improves you is working on the stuff you don't know. So okay, all that said, let's. I'll get my Facebook off the screen and share the screen. Okay. So you should see. Did I spell that word right? Looks weird. All right, so let's do the next one. So everybody sees my screen and everybody's got it all right. All right, so I'm going to invite you to work these problems. They sort of build on each other, right? So go ahead and figure out how many chiral atoms there are, and then you can work from there. But I'm going to stop pretty quick, and I'll answer the first one because that may change your answers on the next ones. Okay, so I'm going to interrupt you. You know what? So vague memories of teaching online last. I taught online over the summer, and I haven't done it yet. I should have set this up already. Sorry, apologies. No. All right. Let's see if I can. Okay, I'm going to launch a poll. How many chiral atoms are there in either of those molecules? The two molecules have the same number of chiral atoms, so just choose for one.
Dr. Jones, could you pull out? Never mind. Okay.
Yeah, sorry. How many? 6 of 13. All right, I'll give you another like 20 seconds. There are 7 people who answered untitled option 1. That is not a, I don't know why that's there.
It made us answer. There were 2 questions on mine.
There are 2 questions.
There were 2 questions on mine, and I had.
It only showed up as untitled options.
Yeah, in order to submit it, we had to.
Oh, okay, okay, all right, okay, good. I was like, what do you guys? Where are you seeing that? All right, 5 more seconds. Get your last vote in here. We got 11 to 13. Okay, so now when I'm sharing the screen, do you guys see my cursor? Okay.
Yes.
All right. I'm gonna end the polling. We got 12 out of 13. So let's see. I'll share the results. We got a vote for 1, a few votes for 2, a bunch of votes for 3, and a vote for 1. We're a divided class. Okay, so I set this up intentionally confusing. So to back up, a chiral atom is going to be a carbon that has 4 chemically different groups bonded to it. So right, like if I bring up, you should be seeing ChemDraw now, right? So we got a carbon there, right? Every carbon's going to have 4 different things on it, like so. So an sp3, so first of all, to be a chiral atom, it's got to be an sp3 atom, all right? It's got to be tetrahedral. So an sp2 atom can only have 3 things bonded to it, so it can't have 4 different things. And moreover, an sp2 atom has a plane of symmetry. I'll talk about that. Maybe I'll talk about that some today. But if anything has a plane of symmetry, then it is not chiral. All right. So tetrahedral carbon here, right? It's got to have 4 different things bonded to it. So it could have an H, a fluorine, a bromine, and a chlorine. All right. So this thing is chiral. On the other hand, this sp3 atom, which also is bonded to 4 things, is not chiral because, right, it's got 2 identical groups bonded to it. There's 2 hydrogens on that carbon, so it's not bonded to 4 chemically different things. So we would call this carbon an achiral carbon. Can't type. All right. So if we go back to the PowerPoint, and you look at these molecules, I think certainly the people who said 4 were looking at that. Well, it's also possible that you were counting in both molecules, and so I meant just to look at like one of these molecules. But if you look at this, if you see a wedge and a dash, your gut will tell you, oh, there's a wedge and a dash there. I need to say that's chiral. But the wedge and the dash don't indicate chirality. They only indicate that, you know, a bond is in front of the screen or a bond is behind the screen. So the chiral atoms are, let me actually go to the next one. The chiral atoms are starred, right? So the carbon, the leftmost carbon with a wedge has an OH, a methyl, a CH2, and an H. That's 4 chemically different things. All right, this middle carbon that's got a wedge and a dash on it, you got 2 methyls on that carbon. So if any carbon has 2 chemically identical groups on it, it's not chiral. So that carbon with 2 methyls, even though I'm showing the wedge and the dash, all I'm doing is showing that the atom's tetrahedral. I'm not saying anything about chirality. So this carbon with the wedged methyl and the dashed methyl is not chiral. And then you get to the carbon with the sulfur and the nitrogen. So this carbon has a sulfur, a nitrogen, a carbon, and a hydrogen. So that is a chiral atom. All right. And then finally, the last carbon with a wedge. Again, this is optically tricky. And as you guys are new to this, I did this. I still do this sometimes, right? Oh, look, it's a wedge. It's chiral. That wedge is a methyl. Well, look, that carbon. So I guess carbon, whatever, you guys see this carbon, has a methyl and a methyl. It's got 2 methyls on it. It's not chiral. So each of these molecules has 2 chiral centers. Questions over here? All right, you guys answer the next couple of questions. Are the molecules chiral, and what's the enantiomeric relationship? I will try to get us hang on a second. No, ignore that. All right, I've launched a poll for if the molecules are chiral or not. No, I haven't. All right, there you go. Okay, so one more needs to vote. Give you another couple of seconds. All right, I'll end it. So we got an 11-3 vote that the molecules are chiral. And so again, they are. I know I'm flipping back and forth. Here we go. Okay, so we determined that there are chiral atoms in the molecules. In general, most of the time, molecules that contain chiral atoms are themselves chiral. All right. So again, the definition of a chiral, something chiral, is that it is not superimposable with its mirror image. All right. So let me go to ChemDraw now. I'll try to illustrate this a little more. All right. So okay. All right, so these two are chiral objects. These are chiral molecules. So if we imagine this line being a mirror, the art is not the art's better, I guess, than it is in the classroom. But these molecules are reflections of one another, and they're not superimposable. And so this you just kind of have to play with to convince yourself. If I take the molecule on the right and I just flip it over, let me copy it. All right, so if I take that structure and I flip it over, flip that horizontally. That's not how you do that. Why did that work? That should not have worked. Oh, it's because it's flipping it. Okay, so yeah, forget what I'm doing with that. That's not the right move. If you take the molecule on the right, and if you like imagine putting a pin down the middle of it and spinning it, this wedged bond that's sticking out, when it turns around, will go back, and the bond that's back will come out. And so this structure, if you spin it in two, will become itself, but it won't superimpose with the other one. And like I said, some of this you just have to play with models. And again, models are really helpful for this. Chem3D, if you can get it on your computer, will work really well. So these two molecules are both chiral, but they look pretty similar. So let me do another one of these. Take all this. So there's going to be one exception, right? So if we take this molecule and now, so if we don't have the trans, the 1,2 trans-dimethyl cyclopentane, if we have cis 1,2, now the two bottom structures are superimposable, right? These two structures are mirror images of each other, and they're superimposable. Okay, so these are chiral. These are achiral molecules. However, if you look at the atoms, the two on the bottom each have chiral atoms. Okay, so that highlighted carbon there has 4 chemically different groups attached to it. It's got an H, a methyl, a CH, and a CH2. 4 chemically different groups. So each one of these molecules, right, those 2 carbons are both chiral atoms. So this is a weird sort of molecule. This is a weird sort of molecule that if a molecule has chiral atoms and it is achiral, it's called a meso compound, right? These are the same structures. If two structures superimpose, if you can make them superimpose, they are the same structure. All right, so down here on this bottom two, all right, these two molecules are the same structure. They each have chiral atoms in them, but the molecules themselves are achiral. All right, so the other way to see this, to be a meso compound, it's basically got to have a plane of symmetry. Can't draw very well. All right, so right there is the plane of symmetry. The left side of this molecule is reflected exactly in the right side of the molecule. Any molecule that has a plane of symmetry will not be chiral. I shouldn't say a molecule. All right, anything that has a plane of symmetry is not chiral. All right, so on the one hand, as you work Wiley plus problems, as you read through the textbook, as you look at my PowerPoints, we'll talk a lot about meso compounds, but they're actually really rare. Okay, and you can sort of know it just as a gut feel. If you look at a molecule and you're like, that's not very symmetric, and it's got a chiral atom in it, then it's going to be a chiral molecule, right? If we go back to these two molecules in the PowerPoint, right, there's nowhere in here you'd find a plane of symmetry, right? The right side of the molecule doesn't look like the left, the top doesn't look like the bottom. If you imagine just taking a plane through the middle of the molecule, you got a sulfur on one side, you don't have a sulfur, like it's just not symmetric. So if you look at something and you're like, that's not symmetric at all, and you see a chiral atom, the molecule itself is chiral. Questions? All right, so the molecules are chiral. Let me stop sharing. I'm going to launch another poll here and give you a bit. So now what I would like you to do is figure out the isomeric relationship between the two atoms or the two molecules. Right? So there's a left molecule and a right molecule. You got your options there. They could be the same structure. That will mean they superimpose. They could be unrelated, which means they don't have the same molecular formula. They could be constitutional isomers, conformational isomers, enantiomers, or diastereomers. I'll give you a couple of minutes on that. I have not launched the poll. I haven't really taught online since last summer, so I promise I'm not as bad at Zoom as it looks. Give you until 2 minutes. Well, there's only 3 of you left. 2 minutes or whenever 14 have voted. All right. So 10 of you think it's diastereomers, 3 think it's enantiomers. All right, so the first thing to do, like I said, you can't really be too careful. You want to make sure they have the same molecular formula. So you got to count the heavy atoms and unsaturations. Like counting the hydrogens is going to be really tedious. So you got an oxygen, an N, and an S on the left. You got an oxygen, an N, and an S on the right. That matches up. So count the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the right. No unsaturations. C10 NOS. That's going to be the same molecular formula. So they have some sort of isomeric relationship. Are they connected the same? And again, you can get to where you do this almost at a glance, but do be careful. So you got an OH. If we just number this chain, right, like. All right, so 1, 2, 3, 4, 5. I'm just going to number the carbons left to right. And then if you can transcribe that over on this side, and it matches up. All right, so on the left, OH is on 2, 2 methyls on 4, N is sitting between 4 and 5, an S on 5, 6 has a methyl. That winds up being exactly the same thing on the right. You got an OH on 2, a dimethyl on 4, N between 4 and 5, sulfur on 5, and a 6 has a methyl. So they're connected the same, right? So now they could be conformational isomers. They're not constitutional isomers. They could be conformational. They could be enantiomers. They could be diastereomers. And the thing you would do is ask, are they mirror images of each other? Well, clearly, as drawn, they're not. But they're not always going to be drawn precisely so they're mirror images, right? If we go back to, sorry, I've got to get out of the annotate. All right, so if we go back to ChemDraw, right, I'm taking care here to precisely draw these things as mirror images of each other, but it could just as well be it could just as well look like that. That is not clearly directly a mirror image of the other two, but it's the enantiomer of one and it's the same as the other. And so you have to sort of manipulate it. If we go back to these two molecules, right, you can see that if you just slide the molecule on the right straight over and lay it over the one on the left, everything lines up. Like in 2 dimensions, let's say, everything lines up. So they're not conformational isomers. And now what you would want to do is look at, do they directly line up? And if they don't, what do you have to do to change that? And a lot of you, I think, maybe did this faster. The other thing you can look at are, all you really need to look at are the chiral centers. So chiral center number 2 here with the OH, that doesn't change, right? The configuration of that one, we haven't figured out yet. Maybe some of you have, but we haven't figured out yet if that's R or S, but it's clearly the same. Methyl on the left, OH wedged, carbon 3 on the right. That's exactly the same on the left. Methyl on the left, OH wedged on 2, 3 on the right. So the configuration of that chiral center stays the same left to right molecule. All right, so we know at that point, because that chiral center stays the same, we know these are not enantiomers. All right, I'll say that again. In going from, if you have 2 enantiomers, the absolute configuration of each chiral center has to change between them, right? So they're the mirror image, so everything has to reflect. When you look in the mirror, everything on you and about you reflects, right? Your left hand turns into a right hand, your right hand turns into a left hand. You totally reflect, all right? So carbon 2 stayed the same, it didn't reflect. So these are not enantiomers. They could be the same and they could be diastereomers. So you go to carbon 5, it's the other chiral center, and again, it's the only one you really have to consider. And now the configuration of 5 does change. So nitrogen on the left, carbon 5 with a dash sulfur, carbon 6 on the right. nitrogen on the left, carbon 5 now has a wedge sulfur and 6 on the right. Okay, so the sulfur and the hydrogen's not shown, but the sulfur and the hydrogen swap places. That means the configuration of that carbon will have changed. Okay, so one chiral center changes, one chiral center stays the same. That's going to give you a diastereomer, right? If they were the same structure, if they were the same molecule, both chiral centers have to change. If they're enantiomers, both have to reflect. Okay, so if at least one changes and at least one stays the same, they're diastereomers. So I want you to get that right, and hopefully everybody understands that. So the next question is, all right, the next question is, what is the absolute configuration of the chiral atoms? So let's just do the left-hand molecule. And I'm going to put up a poll for this. All right, so we're just talking about the left-hand molecule. I should say I've got all of you gathered on another screen. So if I hope I haven't not paid attention to you. If you have a question, just yell it out. All right, I'm gonna give you 45, I'll tell you what, 3 minutes or everybody's voted. All right, last call. Like I said, we're a divided class. That's a pretty nice symmetrical breakdown. So let's take these molecules over and go through them. Because I know this is pretty new. Let me clear my. All right. Because like I said, I know this is a really new skill. And here's the thing. So we're just doing the left-hand molecule. I'll move right up there. And I'm actually going to. No, never mind. I'm not going to do that. Okay. So me write the things you have to do here. You have to assign priority to the 4 groups. All right, so this is what you have to do for that if you're still unsure. Everybody gave an answer, so I assume you have some idea of this. Right, so we're going to assign the priority to the 4 groups. We're going to then orient the molecule so you're looking down the chiral carbon 4 priority group bond. Then you trace a circle 1, 2, 3. If that circle is clockwise, it's R. If it's counterclockwise, it's S. So let's put in the H here. All right, there's an H there that's not shown. And then assign priorities. And the priority goes by atomic weight. So the heaviest atom is 1, the lightest is 4. I hope this will show up on the screen. So that O is going to be 1. The H will be 4. Okay, so if you want to go 1 atom at a time on every chiral center. So O, like the chiral atom, sorry, hang on. The chiral atom is highlighted there. So it's attached to 4 atoms, all right? To be chiral, it needs to be bonded to 4 chemically different groups. So we're not taking into account just the atoms, but this Kahn-Ingold pre-log, it's accounting, it's not really science. And so you go 1 atom at a time. And so O is heavier than C, and that's heavier than hydrogen. So O is 1. O is the heaviest atom the chiral carbon is bonded to. So it's priority 1. The H is lighter than C, right? Atomic weight of 1 versus an atomic weight of 12. So H is priority 4. It's the lowest atomic weight. Now we've got 2 C's, right? So if we just think about that, we got a C there and a C there. So that's a tie. Those 2 carbons weigh the same. That doesn't mean it's not a chiral atom, that the carbon 2 there is not a chiral atom. What it means is we just have to go to the next thing. So underneath each of these, you write what it's bonded to. So C, oh wait, sorry. That the methyl carbon is bonded to an H, and an H. The next 3 things that, right, that highlighted carbon, then we go to the next thing there that carbon's bonded to, and that's 3 H's. Do the same thing over here. Right, so now we're looking at the 3 things on from that carbon. And that is a C, an H, and an H. All right, so the chiral, the right-hand carbon there is bonded to a carbon and then 2 H's. And then again, we just go through atomic weights. And so the right-hand carbon, that carbon that it's bonded to breaks the tie. So carbon is heavier than hydrogen. When you do this, when you write those 3, the next 3 things down, you need to write them in order of atomic weight. We'll see that maybe with the other one. All right, so then that means in terms of priority, this is going to be priority 2. And that's going to be priority 3. Any questions how I did that? Okay. And so now you trace this, well, so now you have to, the way that Kahn-Ingold and Prelog set this up is you're supposed to draw a Newman projection. Properly, you draw a Newman projection looking down the C4 bond, or in this case, the CH bond. It works out that you don't have to do that if, right, if the 4 group is back, if the 4 group is wedged. So if you have a chiral center drawn this way, 2 bonds in the plane, a wedge and a dash, sort of the way you do in this zigzag bond line. If that 4 group is back, you can just trace 1, 2, 3, and you'll get the right answer. It's a little dangerous to do because if the 4 group's not back, or if it's to the side, or especially if it's to the side, you've got to rearrange the molecule, right? If the 4 group is to the side, you have to imagine a Newman projection. All right, so in this case, tracing 1 to 2 to 3, that's a clockwise motion, right? So we're going to say that that is R. Okay, so I took down the polling results. RR and RS got 8 votes. Right, so now it matters what we do on the other one. And I should say here, there's a lot of really funny stuff about doing this, about assigning absolute configuration. And if you were to do this, like there are 2 answers. It's either R or S. If you know it's a chiral center, it's either R or S. So, you know, it's certainly at the end of the exam, if you're rushing to turn something in, like don't leave this one blank. 50-50 is about as good as your, you know, a guessing odd you're going to find in a chemistry exam. So put something down. The other kind of sad thing about it is if you make one mistake, you'll be wrong, right? So let's say I had screwed up the priorities and I'd said that the methyl was 2 and the CH2 was 3, right? If I swap these 2 out, I do everything else perfectly. I just miss that one thing, you know, I get S. If you screw 2 things up, you'll get it right. Okay, so like I said, it's the only way to really analyze whether or not you guys have learned how to do this is to do a large sample size, because I promise it's a lot of tedious stuff. It's like counting how many carbons. If I ask you to do this one time, I don't learn anything by you doing one. So you'll probably have to do a couple. Let's do the second one. I'm going to put the H in, right? There's an H sticking out toward us. All right, so now we've got that chiral carbon and it is bonded to an H, a carbon, a sulfur, and a nitrogen. So now you do just go strictly by atomic weight. There's no ties. Let's do this one. So S is 1, H is 4, N is 3. No, sorry, 2, see? So 2, and then this carbon is 3. Okay, so sulfur is heavier than nitrogen or carbon or hydrogen, so it's 1. Nitrogen is heavier than carbon and hydrogen, so it's 2. Carbon's heavier than hydrogen, so it's 3, and hydrogen's the lightest, so it's 4. And so now what you really should do, to be precise, is turn the whole molecule around so the chiral carbon is in front of the priority 4 group. All right, so really what you've got here, well, this is hard to do over Zoom. I haven't quite worked out. So right now we're at, this is where we are. Okay, so if we look, we're basically looking down the 4 carbon bond. We're exactly turned around. So, sorry. So off the carbon, all right, off the carbon is 1. I don't know if you're following what I'm doing. This is, so if you were to, right now we can draw a pretty easy Newman looking down the hydrogen carbon bond. That's exactly the reverse of what we need to do. We need to have the carbon in front. So you got 2 things you can do here. You can actually physically try to turn this entire thing around, right? We can, let's see if it works this time. So flip that horizontal. And now the H would be behind, right? So now that's, and the bonds would come to the center. So that's what you're supposed to do. The other thing you can do, you're exactly reversed. So over here, if you orient the molecule so that the chiral carbon's in front, priority 4 group is in back, clockwise is R. But if you're exactly reversed, clockwise will be S. So here, right, this takes us 1 to 2 to 3 now. As it's drawn with the low priority group in front, 1 to 2 to 3 is counterclockwise. All right, so counterclockwise normally would be S, but with the 4 priority group in front, it's going to be R. And like I said, you can see that if we actually move the molecule so that if we turn it over so that the 4 priority group is in back, now it's a clockwise, okay? So what I would say is the easiest chiral centers to get are the ones that have the low priority group back, right? Especially if if a chiral atom has a hydrogen, it's only got 1 hydrogen, that hydrogen is going to be 4. If it's back, this is relatively easy to do. The second easiest is when 4 is pointed at you, because then you can just reverse everything. The hardest will be when 4 is on the side, all right? Because then you definitely have to move things. Cool. So this was RR. 4, have you got that right? Anybody have questions about that? Like most of you missed at least one, but I don't know if that's because you didn't know. Like a lot of the 3 rules that you have are pretty simple. A lot of this is just practicing doing it and remembering. The easy thing to do is like here, I could have said, okay, I'm going to leave the molecule the way it is, and then I'll reverse it, and then you forget to reverse it. So
What if the least priority group is on the side?
What happens if it is? You guys want me to give you one of those? I tell you what, real quick, just think about what the chiral, what the configuration for this one is. All right, so this is the molecule on the right. I'll give you I'm not even going to do a poll. Just think about it. What are the configurations of those 2? And then Juliet will do one on the side. Sorry, somebody has a chat. I didn't see it. Matt, we'll do E and Z here in just a second. Okay, so you've worked out R and S. Like I said, as I went through it the first time, the configuration of the chiral atom with EOH doesn't change. Methyl on the left, chiral atom with a wedged OH, CH2 on the right. So this one stays the same. It's going to be R. And then the chiral atom with the sulfur does change. The S and the H swap, right? So S is in back, H is in front on the left molecule. On the right molecule, S is in front, H is in back. Anytime on a chiral center 2 groups switch, the configuration changes, right? So this one's going to be S. You don't have to go through all the other stuff, right? So you don't have to reprioritize it. If you did it correct up on this molecule, you know this one. The other thing is if you know the absolute configurations for a molecule and then you're given an enantiomer or you're asked what the configurations of the enantiomer are, it'll always change. So for the right-hand molecule, for the left-hand molecule, we have RR. So the enantiomer of that molecule, however it gets drawn, is going to be SS. Right? And then for the molecule down here on the lower right, it's RS, so the enantiomer has to be SR. Okay, this is worth practicing. I've got another molecule. I mean, like I said, this is all a voluntary class today. I'm probably not going to end right at 145. I'll end when I get through the second molecule where all of you have gone. Like I will pay attention to that. If all of you sign off, I'm not going to just sit here and talk about absolute configuration to my screen. Let's do, let me build a molecule here. Come on. Okay, find how many chiral centers there are in that molecule, and then is it R or S? Yeah, so I had a question on the chat as this is distracting to worry about it. So what I would say is if you're wondering what's going to be on the test, go look at the exam topics I posted this morning. Specifically, percent EE and optical activity will not be on the test. We would have done it today in class. This is not officially a class. I don't want you guys going and telling the dean that I had class today against orders. You're all here voluntarily. None of this is new. You can leave at any point you want. So I can't put on like a new topic and hold you responsible for it. So no enantio, no percent EE and no optical activity. I probably will show it to you on Tuesday, but it won't be on the test. Another couple of minutes. Okay, so again, the first thing is to assign the priorities. And that's going to be, so nitrogen's heavier than oxygen. So nitrogen's 1. Oxygen's heavier than carbon. So that's 2. Now you've got carbon-carbon tied. Right, so there's a carbon there and a carbon there. So you do your next 3 things. The methyl is going to be H, H, and H. And then the CH2 is going to be C, H, and H. I'm doing this really, I'm taking every step literally. You can certainly glance at that, right? A methyl is always going to be the lowest priority carbon group. You can't have less than 3 H's on a carbon by priority. So technically then the next carbon beats this hydrogen. But if you just glance at it and see a methyl, you can just kind of be like, but don't just glance at it based on total size. You have to go one atom at a time. Okay. I can show an example of that here.
Wait,
Sorry.
wouldn't the oxygen have a higher atomic mass than the nitrogen?
Yeah. Thanks.
No problem. Thank you.
I don't have a periodic table in this room. And I do have that memorized. But so like I said, all right, I'm gonna act like that was in no way intentional. I just totally fumbled that. But if you do that, and it's one thing that like you really need to know how to do this. I want you to know how to do it, but it's a lot like nomenclature. Once you know the basic rules, I promise you'll screw it up sometimes, right? If I ask you 10, if I ask a really good, solid organic chemist to do 10 of these, very few are going to get more than 9, right? You're going to screw up at some point. Okay, so oxygen is 1, you're correct. Nitrogen is 2, and then this is going to be 3, and this will be 4. So the methyl is going to be 4. Okay, so now I'm going to erase that. So now you might look at this and say, well, okay, I got my 3, and 1 to 2 to 3 is counterclockwise. And so here's the trouble. Let me copy this molecule. The trouble with that is that you're not really, there's no real 1, 2, and 3. So if we swap the N and the O here, sorry, that actually does change it. Just a second. That's not the swap I wanted to do. If I swap the dash and the wedge, so keep the nitrogen in front and the OH behind, but just switch which side. Like the wedge on the top molecule, the wedge is on the left, the bottom molecule, the wedge is on the right. But really what that is, we're just canting the molecule a little differently so that the thing on the wedge is not directly in front of the thing on the dash. Like if we really looked at this molecule exactly side on, the nitrogen would be directly in front of the oxygen. It would be hard to write, it would be hard to work with, we wouldn't be able to see what we are. So these two structures here are exactly the same. And I'll prove that to you in a second. Okay, so, and if you look at this, now oxygen is 1, nitrogen's 2, carbon's 3. Now all of a sudden that changes from counterclockwise to clockwise. And in reality, you've got 1 and 2 are in exactly the same place. So we have to turn the molecule. And again, this is one of those things, I don't know how well this works in person, but I'm finding it doesn't work terribly well on screen like this. But what you would do, and since you have to make a change to the molecule, you have to move the molecule, decide to do it in such a way to put the 4 group back, right? We want to move it so that the methyl goes to the back. All right, so I'm gonna imagine taking this molecule, I'm gonna grab the ethyl group, the 3 group with my right hand, the methyl with my left, and I'm gonna pull the 3 toward me and the 4 away from me. All right, so that's what you would do. And if you do that, so the methyl now goes back like that. And yeah, sorry. The methyl will go back like that. The ethyl will be, right, the ethyl will turn to the front. And now the hard thing to see, right, if I do this, the nitrogen is toward me. If I'm pulling the 4 group back, the thing that's in front we'll move over to the left. And the OH, which is behind, will turn over to the right. I hope I have done this correctly. All right, and now your for group is back. So now you have 1, 2, and 3. That's now a counterclockwise circle. The for group is in back. And so this should be S. When I do this in class, the only check on me is you guys. And most of you aren't confident enough to tell me. So now I can. Seriously, I'm not play acting. I'm always a little nervous about these. So that's going to be S. And I can prove to you the bottom one is the same with ChemDraw. Like that's S. Of course, this will be embarrassing. This is not right. Oh, good. All right. So like I said, the key thing there is moving the molecule. And there's a bunch of that operation. I would say that that's a really common thing to need to change, right? Is basically to move 90 degrees. And the thing to keep in mind when you're doing this, and this works for chair to bond line to chair, Newman to bond line to Newman, or working, trying to move the molecule in such a way that you can do an absolute configuration. Those are all things where you really need to anchor your perspective. So you need to, like, my face is right here, and then I'm going to do an operation to the molecule. So don't try to move the molecule and rotate a bond, or move the molecule and flip it over, right? Like, do one thing and then see what that looks like. And then if you need to do something else to it, do something else to it. But don't try to, the more you try to do it once, the bigger the chance is you're going to screw something up. And it's possible to screw that up. Like, you can, if you just kind of forget which way you're turning or something, it's easy to mess that up. Questions about that one? All right, so I'm going to go back to the PowerPoint. Oh, how many stereoisomers are possible for this? I've got a poll. Just ask yourself real quick. I'm not going to do the poll. I'm going to get on to the next molecule. So I think, yeah, RRRS. So how many stereoisomers are possible? Give you like 30 seconds to think about it. All right, so I've actually given you the answer by sharing the poll results again. The way this works, if you don't have isomerizable double bonds, there was a question about isomerizable double bonds, and I'm going to get to that in the next molecule. But if you only have chiral centers, the number of stereoisomers possible is 2 raised to the power of the number of stereocenters. So we've got two chiral centers here. And so that means if you pull this over here, right? RR, SS, RS, SR, those are the possibilities. So there's 4. 2 to the 2 is 4. These are the 4. The assumptions in coming up with that equation are that the chiral centers are independent of each other. So this always represents a maximum number of of stereoisomers, right? If somehow the 2 chiral groups are chained together, so if one changes, the other one has to, that happens sometimes in a ring, then you don't get 4 stereoisomers, right? So, okay, so I know some of you are going to have to take off, but I'm going to go ahead and do this next molecule. If you want to hang around for it, if at least somebody hangs around for it, we'll go through it. It'll be recorded and I'll post it later. If you got to take off, well, you shouldn't have to take off, should you? But if you just want to, I'm going to imagine, if you leave, I'm going to imagine my head you have some other pressing thing to do at 1:45 and it's not personal. So, okay, so how many chiral atoms? Are the molecules chiral? Isomeric relationships, absolute configuration, stereoisomer. Go on all that, and then I'll be back in just a second. Okay, so I've relaunched the poll. How many chiral atoms?
The second question is still showing up as untitled.
Yeah, I can't figure out how to just choose an option. I couldn't figure out how to get rid of it. Although untitled option 2 finally got a vote. It didn't get any votes last time. All right, another 20 seconds or all of you have voted. All right. So most of you said 2, and I'm pretty sure before I get where to go. I'm having trouble arranging things on my screen. All right, so most of you said 2, and if we go over here and look, it's going to be 2. So this time you wrote, like I said, you can't rely on wedges and dashes, but certainly you should look there. You can have a chiral atom that doesn't have any wedges and dashes. Like the atom can be chiral without you knowing where the groups are. So any carbon that's got 4 chemically different groups attached to it will be chiral. And so, you know, a methyl can never be chiral because it's going to have 3 hydrogens. This carbon with the bromine has a carbon, an sp2 carbon, an sp3 carbon, a bromine, and a hydrogen. So that's 4 different things. sp2 carbons can never be chiral. There's a planar symmetry in the carbon right down the middle because it's planar. And it can only be bonded to 3 different things. These 3 sp3 carbons that are CH2s also can't be chiral because they've got two hydrogens which are identical. So then that leaves this carbon with the wedge, or sorry, the dashed OH. So it's got an OH, an H not shown, an sp2 carbon, and an sp3 carbon, 2 chemically different groups. All right, so 2 chiral centers there. So are the molecules chiral? Yeah, so are the molecules chiral? Another 15 seconds, 2 minutes, or everybody goes. All right, so most of you said yes, and it turns out that they are. Again, there's no plane of symmetry that would offset the chirality. So, well, I won't go into that. So you've got chiral atoms in the molecule, and like I said, the overall molecule isn't symmetric. So for a molecule to have a chiral atom in it and not be chiral, it's got to be really symmetric, and these aren't. So let's stop sharing those. No. So let's launch this. So what is the isomeric relationship of these molecules? All right, another few seconds. Okay. So I've moved these to ChemDraw, and again, this is going to be fixed links. Okay. So if you imagine a mirror right here, some people see this easier than other people. I always really struggle with this, but these 2 structures actually are drawn as mirror images. And so the question then becomes, are they superimposable? We decided in the last question that the molecules are chiral. So that means if they're chiral, that means they're not superimposable with their mirror image, which would mean that these couldn't be the same. And it does precisely reflect. So the other answer I see is diastereomer, and they're definitely are diastereomers for this molecule, and we'll get into that here in a second. So because the two structures are mirror images of each other, the only options are that they're the same or enantiomers. And so then what you have to imagine is taking the molecule on the right, well, or you could do it with one on the left, and superimposing all the atoms. So right now you can see how like the 6-membered rings are farther away, the bromines are closer. So you'd have to imagine like flipping it over and then overlaying it so that in 2 dimensions, all of the atoms align. So I'll show you what I mean by that, right? So I'm going to flip this thing over. And it doesn't, this doesn't, right? Yeah, that looks the same, but that's not what, it doesn't flip horizontal very well. In 2 dimensions, both of these structures fit, right? That fits there. And then if we flip that over, if we flip that back over, right, that fits there. So definitely in 2 dimensions, these things fit. Go back to this thing. And so now here's the thing, in going from, right, and going from that right-handed structure to the just flat 2-dimensional structure, as I turn that over, as I turn the right-hand molecule over, anything that's wedged and sticking up is going to rotate to the back. Anything that's back, dashed, is going to rotate to the front. And so this is going to end up looking like this. That's not the right bond. Hang on just a second. Okay. Right. So now if you compare these structures, both chiral centers have inverted, right? So the carbon with the bromine has switched, right? The bromine and the H swap places. That means the configuration switches. That means they're reflecting in each other. The carbon with the OH has switched. And so these are going to be enantiomers. And these are the two easiest ways to draw an enantiomer. Some of you will more easily see the mirror image, be able to draw the mirror image. So if I ask you to draw an enantiomer of a molecule, you might just draw the mirror image. Or you can draw all the atoms exactly in the same place so that they exactly overlap, and then just change every wedge, you know, just swap every chiral center. Wedges to dashes, dashes to wedges. But you got to change all of them. All right. All right, let's go on to the next one. So there are 2 chiral centers. Yes, the molecule's chiral, they're enantiomers. Yikes. Hopefully you didn't see that. Okay, what is the absolute configuration of the chiral atoms and do the double bond? Some of you, maybe you've seen this, but this is where any of you are interested in the isomerizable double bond, we'll talk about it here. So go ahead and do the absolute configuration. Do the left-hand molecule. And there's a poll there. I know I said do the double bond, but don't worry about the double bond just yet. Just do RNS. All right, another, let's say actually, let's go ahead and say 3 minutes. 3 minutes or everybody votes. Okay, last call. All right, so most of you think the one on the chiral center on the left is R. Most think the one on the right is S. So let's go through that. So I confess, I always like to start with the one with the hydrogen back, right? So if you've got a wedge, if you see a chiral center and you've got 2 bonds in the plane and a wedge, that one's going to be easier to do than the others. So if we do priorities here, my phone and my Alexa are blowing up, and I hear my wife running around. I don't know what's going on. All right, so the bromine is 1. Bromine's heavier than carbon. Now this is an interesting tie here. So carbon and carbon tie. And so I'll take you through this. You've seen this, right? A methyl is H, H, and H. When you have a carbon that's double bonded to something, you actually count those bonds twice, right? That carbon, the carbon on the left that's tied with the carbon and the methyl is only bonded to 2 other things, a C and an H. So you count the double bonded C twice. It doesn't really matter here. That carbon's gonna, a carbon that's bonded to anything other than hydrogen is gonna beat a methyl. But that's how this would look. And so this is 2, and that's 3. And of course, hydrogen is in back. And so if we look at this, 1 to 2 to 3 is counterclockwise. So I get S for that. If you were in class on Tuesday, I told you the thing I most commonly screw up when I do this fast is screwing up what clockwise is and what counterclockwise is. All right, so the other one, again, we've got an oxygen that's 1. Oxygen's heavier than the 2 carbons. Hydrogen is in front, priority 4. Carbon and carbon tie, so again, we got H, H, and H. We have exactly the same thing as no, we don't. So this carbon there is actually bonded to 3 carbons. So it wins hands down. So that's 2, and this is 3. All right, and so now 1 to 2 to 3 is again counterclockwise. So you think that's S? No, nobody's. I
I
want
have
to see
a question.
Yeah, hang on just a second. So it's not S because priority 4 group is in front. Right. So you take the reverse. 1, 2, 3 being counterclockwise. If you had it oriented right, would be 1, 2, 3 being clockwise. So this one's R. Okay, who had the question? Sorry, I didn't see it.
The 3rd carbon that we labeled priority 3, how is it bonded to 3 hydrogens?
It's not. That's a good question. Sorry. I get going fast and thinking about the next thing. So yeah. So again, that is an easy way to screw up. You want to accurately represent what they're bonded to. Here it doesn't, like that's a screw up that doesn't matter, right? If I think that's HHH, it doesn't matter because the one up top is CCC. But if the one up top had been CHH, I would, and then had the priorities flipped, it would have changed the answer. So that is going to be RS. So what does that make the chiral centers in this molecule? All right, so we decided that they're enantiomers. And that means the carbon with the OH has to invert, carbon with the bromide has to invert. So RS has to turn into SR. Let's check that. So we got an S and an R. Which one's which? It's not telling us very well. So if I erase the bromine, we're left with S. Yeah. So if I put the bromine back on, I get R back. All right. So that's correct. So it was RS in the left-hand molecule. It's SR in the right-hand molecule. Now the question is, how many stereoisomers are possible for this structure? Yeah, Brent?
Can I answer the question?
Sure, go ahead.
I think it's 4.
So how are you getting 4?
So it's the formula is 2 to the n, and n is the number of chiral centers in the molecule, so it would be 2 raised to the 2nd power.
Yeah. So that's wrong, but it's right in spirit. So chapter 5 teaches 2 to the n, where n is the number of chiral centers. And so if you have a molecule, and again, I've said that there's not going to be new material in this class, so I don't know how I'm going to really, I may not really include this much on the exam, but the other way you can get a stereoisomer is a cis-trans isomerization. All right, so you're right, there are 2 chiral centers, and you can have those be, let me share the results again. Right, so you can have RR, RS, you can have RR, SS, RS, and SR. And so they operate independently, and so that would be 4. We would have the 4 you'd have 2 pairs of enantiomers. You'd have RS and SR, and then you'd have the RR and the SS pair. So those 4, and each there's 2 pairs of enantiomers. Both of the enantiomers in the other pair are diastereomers of either in the first pair. All right, but we have an isomerizable double bond, and I like to put this in the stereochemistry chapter. They usually save it for alkenes, and so but I'd like to put it here. This double bond, and if you look at the name, come on. All right, so right there, that E is telling you about the double bond. All right, and so one of these double bonds is actually isomerizable, which means it can be cis, it could be trans. The way it's drawn here is trans. Right, we've got an H. It just went to, so this will take it back. H and H. Those 2 H's point in opposite directions, so it's a trans double bond. The more precise way of saying this is E or Z, and what you want. This really is new material. This won't be on the exam. E and Z will not be on the exam. Cis and trans will be, but E and Z won't. So what you would do, though, since you're here, I'll explain it, is you look at the double bond and you assign priority exactly the same way. So on the first carbon, we've got a carbon and a hydrogen. So that is 1 and the hydrogen is 2 in terms of priority. On this carbon, right, we have a hydrogen and a carbon. So carbon is 1, hydrogen is 2. If the ones are trans, the double bond is said to be E. If the ones are cis, it's said to be Z. And again, you don't have to worry about doing that on exam 1, but I'm explaining it here. And so that actually adds, so friends, to your point, that adds another independent thing that could change, right? So if you have 2 chiral centers, you can have RR, RS, SS, SR. Now we could have each of those with an E, so that's 4, and then each of those with a Z, and that would be 4 more, right? So there's going to be 8 in this one. But that 2 raising to the power, clearly you should memorize this equation, right? Like I don't want to teach memorization, but this is a lot easier just to memorize. But understand what's underneath that. Every variable that can be one of, could be 2 things, it's going to be 2 to that power. Now the double bond in the ring, this is why I say this is a lot of new material. That double bond in the ring is not isomerizable. All right. The reason is if you tried to change it to trans, you can't now close a ring around it. So it's a pretty complex thing. We'll hit that when we do the alkene chapter. So don't worry about isomerizable double bonds for right now. But yeah, so the answer here would be 8. Chiral center there could be R or S. Double bond can be E or Z, cis or trans. And then this chiral center can be R or S. All right, so.
I have a question.
Yeah.
So for the purposes of the exam, if you ask us how many stereoisomers are possible, do we just use the 2 to the n, or do we consider
just
all
use
other things?
that's what I'm doing right now. I had it, and in fact I put that in the, I'll go edit the exam topic I'm pointing you guys to. Like this is technically new material. I mentioned it, like I slid in a 15-second bullet point about this at the end of the last class, but that's not really, I don't like doing class. I don't like doing exam topic that way. So like if we'd had class today, I was going to talk about this a fair amount. All right. So yeah, you do not have to, you will not have to assign E or Z to an alkene, and you won't have to worry about isomerizable double bonds in a molecule. I ask you how many stereoisomers are possible. All right, so last thing here, and I'll give you a few minutes on this. I do actually speak English. So draw a diastereomer and a constitutional isomer of the 2 molecules shown below. I'll give you guys a bit for that. All right, so I'm going to go to the next slide, and I'm going to show a few examples. So I just said there's 8 possible stereoisomers, right? So I've moved these are our original 2 over on the left. I've shown a couple of examples. So if you're asked to draw a diastereomer and you've got multiple chiral centers, the easiest thing is, change one of them. That leaves all the others the same, and you change one, you get a diastereomer, right? So that structure I just highlighted there, the OH has stayed R, and the bromine has changed to R as well. So that is a diastereomer of either of these enantiomers on the left. And this is what I was going to with the isomerizable double bond. The other thing you could do is isomerize the double bond. So if you have a trans double bond, change it to cis. If you have a cis double bond, change it to trans. Or if that's a ring, you can have cis and trans in a ring as well. And you can change cis, So if you've got a cis ring, change it to a trans, change to a cis. That actually usually involves changing one chiral center and not the other. Right, so that highlighted structure there, the 2 stereocenters have actually stayed the same, right? So as the molecule on the left. So the molecule on the left is RS, R for the OH carbon, S for the bromine carbon. That's the same as in this structure here, but the double bond has changed from trans to cis. So that highlighted molecule is the diastereomer of both of these molecules over here. And then finally, if you want to draw a constitutional isomer, just make one small change. A lot of times students, end up trying to make huge changes. But if you don't exactly nail the number of carbons, say, then you miss it. So all I've done here is I've moved the double bond from being conjugated to the acyclic double bond. I've just moved it across the ring a little bit. So that's a constitutional isomer. There are literally, like 10 to the 20th constitutional isomers for this molecule, probably. So as you get more and more atoms, the number of constitutional isomers scales exponentially. So I have no idea how many constitutional isomers really exist, but it's a lot. And that's all my PowerPoint stuff. So I'll hang around and I'll hang around for a bit anyway and answer questions if you have them. Certainly feel free to leave if you have other stuff to do, but if you have questions, or I'll hang around until there are no more questions or I get really tired.
I have one quick question.
Sure.
So for diastereomers, is it okay if you just keep the line drawing facing the same way and then just change from a wedge to a dash?
Yeah, sure.
For one of them?
Yeah, so
okay, so you can
here, let me
you can just change.
Let me go back over to right, so you could have just taken this one, keep it drawn that way, and then just changed that one. That's going to change that R to an
okay
S,
yeah, I did
right?
that.
Yeah, that's fine.
Okay, thank you.
You bet. Anybody else? All right, I'm gonna go get some lunch. You guys stay warm, and I'll be on. I'll announce some times that I'll be on tomorrow, and we'll do something like this again. So.
Could I ask one quick question? I apologize.
Yeah, no problem.
So, the naming with the S and R on the one we did, the last molecule we did, could you explain to me how you named that and how you determine? I just don't know how to put that. It was kind of confusing.
How to name that molecule? So hang on.
With the S and the R in front of it.
So how to name this one?
Yeah, you had it on ChemDraw. You did the ChemDraw naming tool, and then I just got a little confused with the
Yeah. So I'm gonna show it to you, and I'll try to walk through it. What I will tell you is I would not ask you to name this molecule. This is I wouldn't.
Okay.
I wouldn't try to name this molecule. And in fact, I had trouble figuring out where like what went where. So it's being named as a cyclohexenol. So the parent for this is cyclohexene, right? So 6-carbon ring with an alkene in it is cyclohexene. As an alcohol, as a cycloalcohol, the carbon with the OH is by definition carbon 1. And then this whole thing is being named as a substituent to that, right? So it's 2. So carbon 1 has the OH. Carbon 2 has the rest of this, and they're calling that. So the double bond is E. The chiral center is S. So it's a 1, 2, 3 bromo, 1 ene.
So the entire thing is an S, the entire substituent?
The entire substituent, the S the substituent only has 1 chiral center. So the rule in putting R and S into names is if there's only one, then you just say S or R. If there's, let's see, I can maybe do this. I tell you what, let me close out of this. All right, so right, so if we, all right, so if there's one chiral atom, right, it just says R. So R octan 3-ol, or you could say R 3-octanol.
So there's no number associated with it?
Right, because there's
The only
only,
reason I asked,
what's that?
the only reason I asked is because on like the Newman projection worksheet, I was looking at the answers, and they had like, it was like what's an example?
Yeah.
Like 2S, 3S in
Right.
parentheses.
So
3S.
two things about that. Like I'll look at that. You guys can check if you worked you didn't. I don't know why I put that in the. Probably because I just did a chem draw, like tell me what the name of it is and paste it in. But on that's a chapter 4 worksheet. So if you didn't work those, it's not like, I'm not going to really back up. I'm not even really going to grade those for accuracy anyway, right? I'm going to look for people who are really confused about something fundamental and try to correct that. But if you turn it in, you're going to get some credit. Now, in this molecule, I'm pointing, yeah. So in this molecule right here, you don't have to put a 3 with the R because there is only 1 chiral center. But watch what happens if we get a second chiral center. So watch what happens to the name when I put this methyl on. All right, so now there's 2 chiral centers. And so if there's 2 or more chiral centers, you have to tie the R and the S to the number of the carbon.
Gotcha. All right, that makes sense. I appreciate it.
Yep.
And do you have time for one more? I'm sorry.
Yeah, no, it's fine.
So on the Newman's worksheet, one of the molecules, it was a Newman projection with it was a cyclopentane.
Yeah.
So I got the structure correct in 2 dimensions, but I wasn't sure how to do the wedges going off of the
yeah, so let me
the pentane. Cyclopentane.
let me see if I can bring that up. Oh, come on. Why is it so big? All right. So this one here, right?
Yep.
Okay. Pull that into ChemDraw and work with it some. Okay, right. So the easiest thing to do probably is to number that.
Yep.
So I'm going to number the front carbon is 1. I'm going to say the back carbon is 2. All right. So we're not going to see 2. That makes this 3, 4, and 5. And so now, so 1 and 5 are bonded. And like you said, that becomes a cyclopentane. Okay. And so now you sort of define where your I is. And I'm going to say, well, you can see my cursor. I'm going to say I'm looking this way. And so I'm going to number this. All right. 1, 2, 3, 4, and 5. And then what I'm going to say is that I'm going to say I'm taking the molecule and I'm just rotating it over like this. So up, like if I look at the front carbon, the methyl is up relative to that H. And carbon 2 has 2 methyls on it. So carbon 2 is pretty easy. It's going to have a wedge and a dashed methyl. Carbon 1, I'm going to say that methyl is up. And so it will be up, and then we'll get a dashed H. Right. And it actually is important because carbon 1 ends up being a chiral atom. And so you sort of have to keep that in going over the way I numbered that. You want to turn it so you're looking down the 1-2 bond.
Okay.
Right.
Yeah, because I was under the impression that like I guess the one connected to the 3 carbon and the one connected to the 5 carbon had to be wedges because they were coming off of the right side.
Yeah, no, so I mean, if you did, you could do it that way, and then you'd wind up yeah, you could do it that way. Trying to think what has to happen.
But it just felt wrong, like because I haven't seen too much of
right.
Like
Yeah,
wedge
so if we did it this way, well, and actually they wouldn't be, so they're gouged to one another. So 5 is down, 3 is up. And so it would be, the way you'd have that would look like this. My mouse at home is not very good. All right, now when you have this, and again, you've got your 2 methyls here that really don't matter. And then on this one, if you did it that way, now you're sort of looking at it left to right. Carbon 1 is going to be there. Like that would be fair. You would have had it. That would be an acceptable drawing. Like if you just said 1 is in the plane. But it's, I don't know. Like I said, it's a lot depends on how you turn things, and there's no absolute right or wrong in how you do that. You just have to, every way you draw it has to be consistent with that thing. So what I said was, or if you want to think about it the other way, I took the Newman projection and I just turned it down like this so that 1 went down and 2 came up. Okay. You can absolutely like turn it left and right so that 1 went to the left and 2 came to the right. It's just once you make that change, then you really have to, that's the only change you get to make. And then everything else you draw has to fit in with that.
The way I kind of thought of it, and this is probably an error on my end, but like so when I draw my Newman projections, or when I draw from a Newman projection, I just draw like a straight line just for the 1 and 2 carbon.
Yeah, I do the same thing.
And then I like in that instance, I would have put, the hydrogen going off to the left dashed, and then I put off of the 2, I put the 2 methyls, which I didn't dash. I dashed only 1, or I dashed 1 methyl, and I had 1 as just on the plane.
Yeah, that's
and then
fine.
Then I wedged the 1 going off the 3.
Yeah.
So that's Yeah.
No, I think that sounds, I mean, I'd have to, I can take a look at it. Like I said,
I know it's hard to explain too.
I probably won't hit the stereochemistry all that hard on that as I go through it. Like I'll be looking for errors that are a lot more fundamental than that. Like honestly, if you had drawn the enantiomer of that compound, at the point where I made that assignment, I'd be fine with that. So
gotcha.
Yeah.
Sweet. All right, I appreciate it.
That's the other thing.
I
mean, even on the exam, right? Like the biggest thing is, did you see that it's a 5-membered ring? Then did you put all the substituents on the right carbons? And then the last thing, like, so again, even on the exam, if you draw the enantiomer, that you're gonna have some sort of grade penalty, but you're going to get most of the credit on that. Like that's the most subtle change you would make.
Okay. All right. I appreciate your help.
Sure.
All right. Have a nice weekend.
You too.
Bye-bye.
I have a question, Dr.
Okay.
Jones.
Yep.
When it comes to naming a cyclic ring, how do you know when to, like, what do you number first?
So there's two rules there, and they're a little, right? So if we put that in, all right, right. So you could imagine naming this 1, 3, 4 or 1, 2, 4. Or I guess you could imagine naming it 1, 4, 5. You always do, like, one of those carbons has to be 1. And the one you choose to be 1 most of the time is the one that gives you the lowest overall numbers. So, right, if we do structure to name, this is going to be 1, 2, 4, because 1, 2, 4 is lower. That's a lower number than 1, 3, 4. All right, but watch what happens if I change this carbon to an alcohol. Now, and this is one of those things, and I try not to. I'm not going to make any promises. I try not to put this on. I try not to trick you up, but for cycloalcohols, the OH carbon is always 1, no matter what else happens. Right? So the carbon with the OH, that's 1, and then that's going to make this one 3 and that one 4. Right? So you'd go this way because you get a 3. If you go this way, the lowest number is 4. Does that make sense?
Yes.
So if it's not an alcohol, you just like do the lowest number you can. Like one of them has to be 1, and then go whichever direction gives you the lowest number. If it's an alcohol, that carbon is 1.
Okay. Thank you.
You bet. Are you good?
Yeah, sorry.
All right.
Okay.